The idea in this video is fairly straightforward, and in fact, we really already know most of what we need to talk about this idea. A linear combination is just a way of combining two or more vectors using the properties about vectors that we already know. Let's do a quick review. I know that if I have a vector u equal to 3, 1, and a vector v equal to -1, 2, that I can add those two vectors together by just adding their components. That becomes 3, oops, it's not a fraction, 3, 1 plus -1, 2, and that, I'm doing the long way here, just to remind you of what's involved. 1 plus 2, and that gives me 2, 3. So this is vector addition, and we know about vector addition. It takes the real number components of each vector and just combines them into a new vector. The other thing I can do with vectors is I can scale them. So for example, 2u is just 2 times the vector u, which is 2 times each of the components of u. Again, this is more detail than you really need to show, but just as a reminder. And again, not a fraction. 6, 2 results in that vector there. If we pull these two ideas together and I scale both vector u and vector v before I add them together, I might get something like this. 3u plus 2v is 3 times the vector u plus 2 times the vector v, occupational hazard, making these into fractions. That's going to be the vector 3 times 3, 3 times 1, plus the vector 2 times -1, 2 times 2, which is 9, 3, plus -2, 4, and that's 9 plus -2, 3 plus 4, which ultimately gives me 7, 7. What I have here, 3u plus 2v, and the result of the actual operations that we did here to get to the final vector here, this is called a linear combination of two vectors. I'm not actually restricted to only working with two vectors. I think I'll go to another screen. Let's say I have the vectors v1, v2, v3, up to vn. That's n vectors. That's a fixed number of vectors, but I don't know what the fixed number is. I can combine these. Let's also say I have a1 and a2 all the way up to a sub n. These are all different values and that they're all real numbers. In other words, they're all scalars or can act in that capacity. I have these vectors and I have these scalars. I can take any combination, a1 v1 plus a2 v2, and so on, up to an vn. And the result, once I know what it is a linear combination of the vectors in this collection of vectors here. It's worth noting that I could instead, if I wanted to, say a1 v3 plus a5 v2 and so on, but it's not it's really hard to say what might go here. There's no sequence, there's no pattern to my annotation here, so it's getting a little crazy and mixed up. Since I don't know what these values are, it doesn't really matter what order I use them, and if I use them in the same order as the vectors, and I put the vectors in order by their subscript, then there's a way that I can write the shorthand, and that is to say that this is the sum of all a sub I, v sub i's, where I goes from 1 up to n. So we have that sigma summation notation again. And this way of writing this is just more compact and takes up less space on the page than this form here. In addition to the new vocabulary linear combination, this vector here, which results from adding together vectors that have been scaled by real numbers, this is a vector. In addition to that vector, which is a linear combination of other vectors, we have some other new vocabulary, and that is to say that in this context, we call the scalars in this list here weights. Now the order of the weights aside, I'm actually going to erase this second one here because it's not instructive and it's just taking up space on the screen that we can use for other things. With the weights, the order of the weights notwithstanding, right? The linear combination I have written here in the shorthand annotation I've used here, I've gone all the way from 1 to n, which suggests I need an a sub 1 and an a sub 2 and an a sub 3, all the way up to a sub n. That sort of implies that I need to use every single vector. And that's partly true if you consider that a could be a sub I, a sub m, a sub j, whatever, some a in this list, including a sub 1 or a sub n. Those could be 0. So I might, in fact, have a sub 1, b sub 1, plus a sub 3, b sub 3, plus, right? This makes it look like I'm missing a sub 2, v sub 2 here. But in fact, all I'm really saying is that a sub 2 equals 0. So in a sense, once I know what my vectors are, when I write a linear combination of those vectors, I'm using every single vector in that set of vectors, in that collection of vectors. It's just that some of my constants, some of my weights may be 0, and so I may leave some out, right? I may not write, for example, let me rewrite this a little bit. I don't need to write plus 0 v sub 2, right? I don't need to include this. But what leaving it out implies is that a sub 2 is 0. So I have used all the vectors in my set of vectors. Right? I've used all of these vectors in writing this linear combination, even if it appears that some of them got left out. I want to point out very briefly here too that I'm not necessarily in Rn here, because although it kind of looks like I'm in Rn because I have n vectors, in fact, what Rn means would be that each one of these vectors has n components. And that's not necessarily the case just because I have n vectors. I could be in R3. I just have n vectors with 3 components each. So I'm going to say that I'm in Rm here just to distinguish that the number of vectors I'm playing with and the vector space that I'm working in are don't necessarily have the same dimension. Now, we've already established that Rm or Rn or Rk, whatever dimension we happen to be in here, we've already established that this is a vector space. And what I've done here is, in fact, I'm going to erase this next line, this last line here again, because again, it's a little bit confusing to leave it on the screen. This is a vector space, and when I play around with combinations of vectors from that space, the result is another vector in that vector space. Okay, let's do an example here. I've got 2 vectors, v1, which is 3, 1, 2, and v2, which is 0, -1, -1. These are in R3. And I have 2 weights, 2 scalars, a1 equals -2 and a2 equals -3. I want to take a look at what vector is formed by the linear combination of a1, v1, and a2, v2. The answer is simply -2 times the vector v1, which is 3, 1, 2, plus -3 times the vector v2, which is 0, -1, -1. Now, of course, I could write this as just -3 here. That would be absolutely fine. So I'm going to get -6, -2, -4. Now, since I'm writing this as a minus, I'm essentially distributing that negative. I'm going to get 0, 3, 3. And when I combine these, I get -6, -5, -7. That's the vector that results. So the linear combination of these weights with these vectors in this order is the vector -6, -5, -7. Another kind of question you might see at this point is, if I give you the vector 6, 1, 3, can you find a linear combination of the vectors v1 and v2 that produce that vector? And sometimes it's really easy to see by inspection what the two weights might be, and sometimes it's not. But it does have to have this sort of form. I'm going to have a scalar or a weight times 3, 1, 2 plus a weight times 0, -1, -1. And whatever those weights are, I need the result to be 6, 1, 3. So I might ask myself, it's kind of handy to have this 0 in here, because anything times 3 plus anything times 0, this is going to be the resulting component here that contributes to the 6 is going to be 0. So that means this one has to be a 2, because now I have 2 times 3 is 6 plus anything times 0. So that's how I get my 6 there. And then I have 2 times 1 is 2 plus something times -1 is going to give me 1. 2 minus 1 is 1, so that's going to be a 1. Double checking with my third component, I get 4 minus 1 is 3. So in fact, I have found a linear combination of the two vectors v1 and v2 that produces the vector 6, 1, 3.